First up, I would like to thank the Academy for giving me opportunity to speak here. So I'll talk about heavy ion collision, which help us to probe the QCD phase structure. Okay, so this talk has two parts. The first part is introduction. So I'll try to introduce this research area to the general audience. The second part, I will discuss the result where my contribution will be there. So as you all know that the visible matter is made up of atom. Everything in this room is made up atom. And atom is further made of nucleus and electrons. Electrons is a truly fundamental particle. You cannot divide it further. However, the nucleus is made up of proton and neutrons. Okay. And the neutrons and protons are also not a fundamental particle. They also made up of quarks. So each proton is made up of 3 quarks, neutrons is also made up of 3 quarks. So like electrons, the quarks is also a fundamental particle. As per today's knowledge, you cannot make it further divide it. So there are 17 elementary particles in the standard model of particle physics. You can say these are the building block of our universe. Now if we talk about the quarks, so there are 6 types of quarks, namely up, down, charm, strength, top and bottom. And they differ by their masses, their electric charge, and they also possess a color charge, you can say colored degrees of freedom. And how they interact? The quark interact by exchanging a gluon particle. This is called the exchange particle. It also contains a color charge and it's massless. And the quantum theory that describes the interaction between the quarks through the exchange of gluons is known as the quantum chromodynamics. In short, it's a QCD. Now, according to the QCD, the potential energy between the two interacting quarks has 2 terms. First term is a Coulomb-like term. It's inversely proportional to the distance, and it's the attractive term. And second term is linearly proportional to the distance between the quarks. So if you plot this potential as a function of distance, as you can see from this here, when the distance is low, the first part will be dominating, that is the attractive part. As the distance is increasing, the second term will be dominating, the repulsive part. Okay. Now what happens if you try to separate 2 quarks which is bound within the hadrons, like here, there is a meson, it's a quark and antiquark pair. And if you, by giving energy, if you try to separate the energy with the increasing distance, the energy between these 2 quarks will increase, and you create a flux tube which contains a lot of energy, and this energy will be get converted into mass, which will create a new quark-antiquark pair. So eventually, you started with 1 meson and you end up with 2 new mesons. So you don't get a isolated free quark. So the quarks are always confined within the hadrons, and we are interested to study a matter where quarks are deconfined. Okay, so how to do that? So if you look back again here, the QCD potential, this alpha s is a strong coupling constant. It's a constant, but actually it's not a constant. You can show the alpha s changes with changing the momentum transfer in the reaction, or you can say the energy transfer. So it is actually decreasing with increasing the momentum transfer. So it was predicted that if we create a high temperature and or a high energy density, then the alpha s could be very small, then this potential could be very weak, and you may create a deconfined quarks and matter that gives rise to a new state of matter called Quark-Gluon Plasma, and this phenomenon is known as asymptotic freedom, and it was the subject of Physics Nobel Prize in 2004. Now how to do that? How to create the high temperature and energy density in lab? So before that, we like to go the further prediction from the QCD. So this is the QCD phase diagram. When we say the phase diagram water comes in our mind, right? We know at what temperature and what at pressure there is solid, liquid or gas. And if we talk about the phase diagram of water, the fundamental interaction that determines the phase structure is the electromagnetic interaction. And the QCD phase diagram it is a strongly interacting matter. So it is a conjecture phase diagram. Very little we know about it. This is the temperature versus baryon density is plotted. This is the simplest form of QCD phase diagram, which can be probed experimentally. And the QCD predict that if you increase sufficiently high temperature or high baryon density, you might create a deconfined phase of quarks and gluons, which is Quark-Gluon Plasma. At low temperature, you have a hadronic phase. Okay. Now, the QCD also predict, particularly lattice QCD, this temperature, the transition temperature here, like at 0 baryon density, is of the order of 165 MeV, which is huge. It's 10 to the power 12 Kelvin. If you compare the sun's core temperature, it is just 10 to the power 6 Kelvin. So we need to create that amount of energy, temperature in the lab, so that we can study the QCD phase diagram in laboratory. So my research goal is the experimental exploration of the QCD phase diagram using heavy ion collision. Okay. Now this is a relativistic heavy ion collider where I am working. So this is situated in Brookhaven National Lab. So what happened? We have a ion source here, and ion source get accelerated, and we let me see. And then we have a big accelerator here, which collide two ion beam. Here, generally we use the gold ion. Ion means we strip off all electrons from the atom, and you get positively charged. And you can see there are 4 different experiment was there. All of them are actually not running. Only the star experiment, this one is running where I am working. So what we do, this colliding energy we can vary. So maximum colliding energy, center of mass energy, is 200 GeV in our case in this accelerator. So if we vary the colliding energy, we can actually vary the temperature and baryon density in this QCD phase diagram. So you can probe the QCD phase diagram by varying the colliding energy. So this is star collaboration. If you try to, this is the 1 kilometer is the diameter, and then if you look at the star collaboration, so there are 76 institutes from 14 different countries who are working, total 750 collaborators. So this is the map where the location of each institute is given. There are few from India. So you can see from this map that sun never sets in this collaboration. So now talking to my contribution of the research. So I will be presenting very selected result from this experiment where I have contributed. So first is properties of Quark-Gluon Plasma. First we will see whether we have created the Quark-Gluon Plasma and what is the properties. And second is what is the minimum energy needed to create a Quark-Gluon Plasma. Okay. So first I will define a quantity called azimuthal anisotropy. So as I mentioned that we are colliding two nuclei. So let's say they are moving along z direction. One is going positive z, one is negative z. And when they collide in the transverse plane, then the xy plane, you can see there will be an overlap region. In this case is a non-zero impact parameter. So overlap region is anisotropic, it's an ellipse type shape, right? And when a collision happens, a new particle will form and they will start interacting. And the interaction will give rise to pressure, and because of this anisotropy, the pressure gradient along x-axis will be more compared to the y-axis. So produced particle will feel more force along x-axis compared to the y. So if we plot the momentum distribution of the produced particle, we will see the anisotropy in the momentum phase also, right? And this azimuthal anisotropy is a measure of anisotropy in the momentum distribution, which can be measured if we decompose the produced particle azimuthal distribution in the Fourier series. And different Fourier coefficient will give you different order of anisotropy. Here we are interested in the elliptical shape. That is why we will talk about the second order Fourier coefficient, that is called elliptic flow. So This is the result. So, we measured this V2 parameter or elliptic flow for different identified hadrons. So, the left hand side is the non-strange hadrons, the proton and pion. Right hand side is the strange hadrons, the omega and phi. They are purely made up of strange quarks. Then V2 is plotted as a function of transverse momentum. So, what we see at the lower transverse momentum, the lighter particle like pion showing the higher V2 compared to the proton. Okay. And as you go to the intermediate PT, the proton showing the higher V2 compared to the pion. Similarly, we observe for strange hadron omega and phi. Omega is heavier, so it's showing the lower V2 compared to the phi, and then again it is showing higher V2 and 1. So, why I have chosen these two? So, this is non-strange and strange, but this proton is a baryon, pi is a meson. So, here omega is a baryon, phi is a meson. So, in the lower PT we see as a mass ordering, which can be explained by hydrodynamics evolution of Quark-Gluon Plasma, but the intermediate PT we see there is a particle type dependent. So, protons and omega, they both are baryon, although their mass is different, but if you compare the both axes, they are same almost. For pion and phi, they are meson, so their mass is different, but they are giving the same V2. So, this particle type dependent actually can be explained by the hadronization of through the quark coalescence. So, if there is no QGP, then there is no question of hadronization through the quark coalescence. So, this particle type dependence or baryon meson separation, we can say this is the evidence for formation of Quark-Gluon plasma. Now, further I will show here same quantity for many different particles, strange and non-strange. Okay. So, this y-axis is now V2 scaled by number of constituent quarks. So, this is 2 for meson, 3 for baryon, x-axis is transverse momentum scaled by constituent quark. And you see that intermediate PT, the baryon meson separation is gone and all are showing the similar V2. This scaling can be further improved at the low PT as well if we plot this x-axis is the transverse kinetic energy divided by NQ, and you see the nice scaling. And this scaling is considered as evidence of collectivity among the constituent quarks. So, here the hadrons we have selected are made of up, down and strange quarks. So, we can say that this plot suggests that there is a collectivity among the up, down and strange quarks. So, we ask this question, what about the heavy charm quark? Do they also exhibit collective behavior or not? Charm quark mass is 1.3 GeV approximately, where the up down is 2 to 4 MeV. Okay. So, we measure the V2 for D meson, which consists of one charm quark and one light quarks, and again we applied the same technique, the NCQ scaling plot, the V2 divided by NQ as a function of transverse kinetic energy scaled by NQ, and the blue data points are D0, and you can see they also follow the scaling. So, this measurement, which is done at gold-gold collision 200 GeV, tells us that charm quarks also exhibit collective behavior. Okay. Now, from the measurement of the charm quark D0 V2, we can extract the diffusion coefficient of the charm quark in the QGP. The diffusion coefficient means how quickly something dissolves in a liquid. For example, if you add some drop of ink in the water, how quickly it dissolves. Okay. So, how do we measure the diffusion coefficient? So, it is a combination of both theory and theoretical prediction and experimental measurement. So, we take the help of the idea of this Brownian motion. You know that Brownian motion, the larger particle undergo random motion in a liquid. So, here you can say that these black dots are light quarks that made up QGP, and the yellow dots are the few charm quarks, and they are undergoing the Brownian type of motion. So, if we measure the collectivity of the D meson, we can extract the diffusion coefficient. Okay. So, this is what I have shown here. So, again I am showing the data of D0 D meson V2, and I am showing the comparison with two theoretical model calculation. This black one showing that charm quark V2 of D0 without assuming the diffusion of charm quark, and you can see clearly that is under predicting the data, it cannot explain. If we include the diffusion of charm quark and with the diffusion coefficient between 2 to 5, it can nicely explain the experimental data. And this predicted value or this extracted value 2 to 5 is also consistent with the predicted by the lattice QCD, which okay. Now the last topic I will discuss the what is the minimum energy needed to create a QGP. So far I was discussing the result in gold-gold collision at 200 GeV. Okay. So here again, so we tried to look at the NCQ scaling plot. If scaling is hold, then the QGP is there. If there is a breaking of scaling, so there you can say that possibly no QGP. So in the star we have collected data starting from 200 GeV to 3 GeV, okay, by varying the colliding energy. So this is the 19.6 GeV. You can see there is a nice scaling, all particles showing the same after properly scaled by NQ, then 17.3 GeV, and up to 7.7 GeV you see there is nice scaling, okay. So you can say up to 7.7 GeV there is evidence for formation of QGP. And below 4.5 GeV we see that the scaling breaks, yeah. Although we are limited by the statistics, but still you can see here these are the even this V2 become negative. So there is no scaling at this lower energy, and between 4.5 to 7.7 GeV there is a transition region which needs to be further explored. Okay, so let me summarize. So there is a evidence for formation of QGP for up to 7.7 GeV and above that, and we have seen that in QGP there is a collective behavior among the constituents of quarks, and the QGP signature disappear at 4.5 GeV. I will finish by showing the QCD phase diagram again. So our aim is to exploration of QCD phase diagram. So this temperature versus baryonic chemical potential plot, I have added many dots here. So starting from this 200 GeV to 3 GeV. So each dot corresponds to the different energy where the star has collecting data. So we are analyzing all this data to precisely measure the properties of QGP. So stay tuned for the new result. Thank you for your attention.
Thank you so much. Questions?
Phase diagram, yeah. So it was a prediction, but still now experimentally we are looking for it, but there is no concrete evidence that it is there. So this QCD based model predict that this transition is a first order phase transition, and lattice QCD predict that at 0 MeV is a crossover. So there must be some point where the first order phase transition ends. So this is known as the critical point, but experimentally it's not found yet. Yeah. So in STAR we have already submitted a paper. So there are some hints of deviation at 19.6 GeV from the non-critical model, but still we cannot say there is enough evidence for critical point. Yeah. So the upcoming experiment, the CBM, the Germany Fair facility, they might be useful to look for even higher baryon density, whether there is a.
Thank you then, Dr. Nasim.
Thank you.